Yes. Hello students. So previous class we derived an equation for delta G and delta H and delta S of cell reaction. So today we can start with the problem. So the question is the EMF of a cell. They given the cell. It is PbCl2 in aqueous KCl solution. 1 molar Hg2Cl2, then Hg. So this is the cell that they are given, and which having an EMF. EMF of the cell is given 0.5357. 5357 volt. Temperature also at 298 Kelvin increases with, that means EMF of the cell increases with the temperature. That is nothing but change in EMF with respect to temperature. That we can say dou E by dou T. Dou E by dou Tp at a constant pressure is 1.45 into 10 raised to minus 4, 10 raised to minus 4 volt per Kelvin. So that's data they given. Now they ask you to find delta G, delta H and delta S. Delta G, delta H and delta S needed to find. Okay. So let us start. Now here from the equation you can understand now lead will undergo oxidation. Lead gives lead 2 plus, right? So overall reaction you can represent like this: Pb plus Hg2Cl2 gives PbCl2 plus Hg. PbCl2 plus Hg. Yes, is there, so if you balance it, you will get, yes. This is the overall reaction you can say. So here Pb undergo oxidation to Pb plus 2 and Hg in the plus 1 oxidation state is going to reduce to 0. So that's oxidation reduction for lead undergo oxidation and mercury undergo reduction. So here number of electron involved is something that you have to check. Here now increase in oxidation number from 0 to 2. That means 2 moles of electron are involved. So here also you have to make it 2. Then only reaction will be carried out completely. So here 2 moles of silver now is produced, 2 moles of mercury is producing. So 2 moles of electron is involved in the reduction. So N number of electron involved will be equal to 2. So this is the data we need. Let us start by calculating first delta G. Delta G is equal to, we know the equation, minus N of E cell. Minus N of E cell, where N is we already saw it is 2 and F is Faraday's constant 96500 into E cell, we already they given 0.5357. So substitute the value, you will get an answer that is one minus 103 minus 103 390.1 joule. So here now please now remember what's the how you got in joule. It is now here Faraday 96500 coulomb is the unit, E cell in volt. So remember volt into coulomb. Volt into coulomb, that we can represent in terms of joule. So here that's how now we can easily convert it into joules as well. So we got Gibbs free energy, change in Gibbs free energy is equal to minus 103,390.1. So that's equation. 1 second, I will come back. Okay, so we found delta G. Now find delta H. The equation for delta H we derived in the previous class. Delta H will be equal to NF into T into dou E by dou T. T into dou E by dou T. P minus E. Minus E. That is the equation for delta H. Okay. So anything else we required, everything is given, right? N we know, F we know, T we know, 298 Kelvin, dou E by dou Tp they given, E also they provided. That means you just substitute the value. It will be 2 into 96500 into 298 into dou E by dou Tp. We have a value that is 1.45. 1.45 into 10 raised to minus 4 minus E value already we have 0.5357. So substitute the value, you will get directly delta H. Delta H is equal to 9 minus delta H will be equal to minus 950.57 joule. So that's the value for delta H we got. Okay. So we have delta G, we have delta H, right? So now let us find the next one, that is delta S. Equation for delta S also we derived in the previous class. Delta S is equal to NF into dou E by dou T. Dou E by dou Tp. This is the equation for delta S. N we know this is 2F96500 dou E by dou Tp already we know. Substitute it. 2 into 96500 into 1.45 into 10 raised to minus 4. Apply this, you will get a value around 27.985 joule per Kelvin. Joule per Kelvin. So that is the answer for delta S. So it's very important to remember the equation. Let us recollect delta H is equal to minus N of E cell, and delta H is equal to NF into T into dou E by dou T minus E. That is the equation for delta H, and delta S I told delta S is equal to NF into dou E by dou T. So that is the equation for delta G, delta H and delta S respectively for a cell reaction. Now let us move to the next section, that is thermodynamic derivations of Nernst equation. Thermodynamic derivation. Thermodynamic derivation for Nernst equation. For Nernst equation. Nernst equation we already know, we did the problem as well, right? So now here we are trying to derive the Nernst equation. Okay. So from the thermodynamics knowledge we can derive Nernst equation. We directly went to the equation, right? So let us have a derivation. So we know in a reversible cell, let us represent a cell reaction. AA plus BB gives CC plus DD. Let us this be the overall cell reaction. Let us discuss one reversible cell. Here now we thinking in terms of an equilibrium reaction, where now we know how can you find an equilibrium constant. Equilibrium constant always it will be concentration of the product. If stoichiometry is there, that should be written as power. So it will be like C raised to C into D raised to D divided by A raised to A into B raised to B. So that's the way you can represent the equilibrium constant, right? Similarly, here minus cell reaction we consider in a reversible cell. Let us have an equation for delta G. That is no, we call it as Van Hoff reaction isotope. Van Hoff reaction isotope. So we directly go into this reaction, no, this equation, Van Hoff reaction isotope, which have a relationship between delta G and the concentration of the reaction species that is involved in the cell reaction. So delta G, which is equal to delta G0 plus RT ln. So let me represent the constant part, equilibrium constant part in terms of activity. So it will be like just like A C raised to C into A D raised to D. What this is all about? Here concentration of the product. I express the concentration in terms of activity. We discussed about activity in the previous sections, right? So AC raised to C into AD raised to D divided by A activity A raised to A into activity B raised to B. So this is the way you can represent the Gibbs free energy equation into for a reversible cell reaction. Delta G is equal to delta G0 plus RT ln AC raised to C into AD raised to D divided by AA raised to A into AB raised to B. This is we call Van Hoff reaction isotope. So here we trying to derive an equation, derive the Nernst equation. So we know what is delta G, we know what is delta G0 as well. Substitute the value delta G is equal to N of E cell. N of E cell is equal to, minus N of E cell is equal to minus N of E0 cell plus RT ln AC raised to C into A D raised to D divided by A raised to A into A B raised to B. So that's the way we can write. We substitute the value of delta G. Now next step, divided by NF. We just next step divided by minus NF. You divide. So what do you get? E cell which is equal to E0 cell plus RT. So here since it's divided by minus NF, here minus cancel, here minus cancel. So here it will be minus, right? So minus RT ln RT by NF, because divided by minus NF ln AC raised to C into A D raised to D divided by A raised to A into A. This is B, okay. Here it has to be B. Yes, A B raised to B. So now we got this equation, right? E cell is equal to E0 cell minus RT by ln minus RT by NF ln AC raised to C into AD raised to D divided by A raised to A into AB raised to B. So now almost we there, right, for the next equation. So here for your easy understanding, you can think if the concentration of the solution is actually less, you can think moderate concentration or very dilute solution, then this activity can be replaced by our normal concentration term. So let us have that familiar equation E cell, which is equal to E0 cell minus RT by N of ln A C raised to C into A D raised to D divided by A B raised to B into A raised to A. So that's the way you can represent the Nernst equation. So sorry, just represent the concentration term, our in our square bracket. So you will be more familiar, right? Concentration of C raised to C into concentration of D raised to D divided by concentration of A raised to A into concentration of B raised to B. So now we reached to our more the term that we more familiar with. So here now the case is now you can replace activity by our normal concentration term. If the concentration of the electrolyte is very less, not high. If the concentration of electrolyte is high, then we have to talk in terms of activity. So simply we can represent this. And now let us have the simplified equation. You can convert ln into log by multiplying by 2.303. Then substitute R will be equal to 8.314 joule per Kelvin per mole. Universal gas constant, F is constant, that is substitute, let T be the temperature at 298 Kelvin. So let us simplify the equation. E cell, which is equal to E0 cell minus 0.0591 divided by N log C raised to C into D raised to D divided by A raised to A into B raised to B. So this is our simplified Nernst equation. Similarly, we can derive this is the case for Nernst equation for cell reaction. Now similarly, just the similar way you can have an expression for the electrode potential of an electrode. This is as we did like this for imagine a general electrode reaction as Mn plus plus an electron gives Mn. Let it be M. Sorry. So this is a general electrode reaction where now let us have an equation. Nernst equation we already know. So let us now derive here. So here now just we can go to the equation directly where delta G will be equal to delta G0 plus RT ln. Here now concentration of product. Here concentration of product is metal. So here now generally we taking concentration of metal as unity. So first we can write like this ln or in terms of activity first we can represent ln activity of metal divided by activity of Mn plus. Right. So now just the usual where you can go delta G apply delta G is equal to minus N of E cell, delta G0 is equal to minus N of E0 cell. So apply there minus N of E cell which is equal to minus N of E0 cell plus RT ln AM divided by AMN plus. Now next step divided by minus NF. So you will get E cell divided by minus NF. E cell which is equal to E0 cell minus RT by NF. Now LNM activity of metal we can take it as unity. So it will be ln 1 by activity of Mn plus. So that's why we simplified it. Similarly now you can convert ln into log, which means you have to multiply by 2.303 and substitute the value for R, T and F. We have the equation for not cell, sorry. Here we are talking about electrode, right? So here electrode, because we are deriving an equation for electrode potential, right, of a particular electrode we are talking about. So let us substitute by E electrode. So it will be E electrode, which is equal to E0 electrode minus 0.0591 divided by N log. Now let us bring this up so that it will be plus, right? Log activity of Mn plus. So that's the final equation. So that's the equation for no electrode potential of an electrode. E electrode is equal to E0 electrode plus 0.0591 divided by N log A activity of Mn plus. So here now we are talking about one electrode reaction. That's only different. So let us represent a reduction reaction like this. Mn plus plus an electron gives M. So we are substitute the Van Hoff reaction isotherm delta G is equal to delta G0 plus RT ln Am by Mn plus. Here now substitute the value of delta G. So E electrode, it will be minus NF. E electrode is equal to minus NF E0 electrode plus RT ln Am by Mn plus. You can simplify it, you can have this equation. So now for a general reduction reaction, now how can you represent this if this is thing in terms of reduction reaction where one is an oxidized state, other one is a reduced state. Let us represent like this. One example, Fe3 plus Fe3 plus 3 electron gives Fe2 plus. So in this special case, now what can you do? How can you represent the general way? It will be like E electrode will be equal to E0 electrode minus 0.0591 divided by N. Here number of electron will be 1 because now here Fe3 plus plus electron and by N log. Here think always generally you can say reduced state. Here Fe3 plus to Fe2 plus means as a reduced state. So concentration of reduced state divided by concentration of oxidized state. That's the way generally you can represent. So it will be like Fe2 concentration of Fe2 plus divided by concentration of Fe3 plus. This is the way you can now write the Nernst equation for any electrode reaction. Okay. Similarly, we can have a relationship with the equilibrium constant. How cell reaction and equilibrium constant are related. So let us have a equation for that. Now before that, now you have to understand a cell like galvanic cell like Daniel cell. It's now zinc is our anode and copper is our cathode. What you can see as the reaction progress. As the reaction progress, now the concentration of zinc decreases because zinc is undergo oxidation. Similarly, copper concentration of copper will increase because copper 2 plus ion is converted into copper. So as the reaction proceeds, you can see concentration of zinc decreases, is diminishes, and finally the cell will stop working because the zinc has gone, right? So that's the way remember such Daniel cells, such cells which actually going to stop after after a long time. So that means once the cell reaction will stop, you will get the cell potential as equal to 0. So let us represent the diol cell. Zn gives Zn2 plus Cu2 plus bar Cu. So this is the case that we are talking about. Let this be the Daniel cell. Now we're talking about equilibrium means the reaction where reaction proceeded continuously a point where equilibrium is reached. That means no more cell reaction. So that is the case you can represent here. So let us have a next equation E electrode which is equal to, so let us now represent cell reaction because here we are talking about cell, right? So E cell which is equal to E cell which is equal to E0 cell minus 0.0591 divided by N log. Here remember concentration of oxidized state of anode first Zn2 plus divided by concentration of oxidized state of cathode. It will be Cu2 plus. This is the way you can represent the cell reaction. Nernst equation for this Daniel cell, right? E cell is equal to E0 cell minus 0.0591 divided by n log concentration of Zn2 plus divided by concentration of Cu2 plus. Now, let us think in terms of equilibrium. At equilibrium, now the situation is reached where now there is no more cell reaction, or no, the concentration of Zn2 plus, let me represent like this, Zn plus Cu2 plus in equilibrium gives Zn2 plus Cu. So this is the overall cell reaction of Daniel cell can represent at equilibrium. No, a state will reach where no there is no more no more production of Zn2 plus, no more reaction from Cu2 plus, reduction of Cu2 plus. So that's the situation you can call equilibrium state, where now you can have an equilibrium constant equation. K is equal to concentration of product. Here concentration of metal we taking as unity, so it will be just like concentration of Zn2 plus divided by concentration of Cu2 plus. That's the way you can represent equilibrium constant, right? So concentration of Zn also equal to unity. So this part will be unity. Concentration of product means Zn2 plus only. Concentration of reactant means Cu2 plus only. So that's the way you can think. K will be equal to this. So let us have substitute E cell, which is equal to E0 cell minus 0.0591 divided by n log Kc, where Kc is the equilibrium constant. So we express now the electrode potential, the cell reaction, the EMF of the cell in terms of equilibrium constant now. E cell is equal to E0 cell minus 0.0591 divided by log Kc. We know as the reaction proceeds, equilibrium will be achieved. At equilibrium, cell potential will reach 0. That's the case, we will say equilibrium will be achieved. So E cell will be equal to 0 at equilibrium, where the reactions, the cell stops working. So let us substitute here. E cell is equal to 0 means E0 cell, we have an equation, because this becomes 0 means E0 cell will be equivalent to 0.0591 divided by n log Kc. So this is the equation that you can remember, which is connecting the E0 cell and equilibrium constant. E0 cell is equal to 0.0591 divided by n log Kc, where Kc is the equilibrium constant. E0 cell is the standard EMF of the cell. So that is the equation connecting EMF of the cell, standard EMF of the cell, and equilibrium constant. So today we derived Nernst equation, and we found a relationship between equilibrium constant and the standard EMF of the cell. So next class we can discuss one problem related to this. Then we can move to the concentration cells. Okay, thanks for listening. Let us wind up. Thank you.